There is a stretch of western Montana where, if you know what to look for, you can still find them. Squat concrete stubs standing in the grass beside an abandoned grade, spaced evenly apart, marching toward the mountains until the sagebrush swallows the line. They once held steel towers. The towers held wire, and for more than 50 years, that wire carried hydroelectric power into some of the most powerful locomotives on the continent, hauling freight over 5 mountain passes without burning a single drop of fuel. In June of 1974, a railroad switched it off. Not because it had failed, not because it had worn out. In the middle of the worst oil crisis in American history, with diesel prices climbing every month, a struggling railroad disconnected 656 miles of functioning electrification, walked away, and sold the copper. That decision looks insane from a distance. Up close, it is completely ordinary, because it is the same decision American railroads made over and over for 100 years, in different states for different reasons, with the same result every time. Today, the United States operates the largest and heaviest freight rail network on Earth, roughly 140,000 miles of track, around a third of the nation's intercity freight tonnage, and essentially none of it moves under wire. Not one major freight main line in the country is electrified. Meanwhile, most of Europe's freight runs on catenary. India electrified nearly its entire broad gauge network in about a decade. In China, a single electric locomotive set drags 20,000-ton coal trains under overhead wire as a matter of routine. So what happened here? The country that built the world's greatest freight railroad also built some of the finest electric locomotives ever made, then took the wires down and burned oil instead. The answer is not that America never tried. America tried more than almost anyone. The answer is that every single time it tried, something showed up that made the wire look like a mistake. To understand any of it, you have to start with why the wires went up in the first place, because it was never about efficiency. At least, not at the beginning. It was about smoke. Picture a coal-burning steam locomotive working hard inside a long tunnel. The exhaust has nowhere to go. It rolls backward along the roof, fills the bore, and settles over the cab. Crews came out of those tunnels coughing black. Some of them did not come out at all under their own power. In one notorious case in the Cascade Mountains, a stalled passenger train left its engine crew unconscious at the controls, and only the quick thinking of a deadheading fireman got everyone into open air alive. That is the problem electricity solved first. A motor makes no exhaust, so the earliest American electrification appeared exactly where the smoke was worst. A tunnel under a city, a mountain bore, a terminal where local ordinances banned smoke inside the city limits. The pattern held for decades. In Appalachia, one coal road wired a 52-mile stretch of 2% grade around a single-track tunnel where trains crawled at 6 miles an hour and delays stacked up for hours. Another wired 134 miles of coal main line in 1925, built its own generating plant on a river to feed it, and ran locomotives so powerful they were the wonder of the industry. And in the Pacific Northwest, one railroad went further than anyone. 2 separate electrified divisions, hundreds of route miles apiece, strung across the Rockies and the Cascades and fed by mountain hydroelectric dams. On paper, it was magnificent. In practice, there was a problem nobody ever solved. The 2 electrified sections were not connected. Between them sat 216 miles of bare track. Every through freight had to swap locomotives twice. Notice what all of these have in common. Not one of them was a national plan. Every American electrification was a surgical treatment for a specific local ailment. A tunnel, a grade, a city, a bottleneck. That is the opposite of how it worked everywhere else. In most of the world, the state owned the railway. Electrification was national industrial policy funded from the treasury, justified by strategic goals, and by the simple fact that many of those countries had no oil of their own and plenty of coal-fired or hydroelectric generating capacity. Wires were something a government decided to build. In America, wires were something a corporation decided to buy. There is one glaring exception, and it proves the rule better than anything. In the Northeast, one railroad built something on a genuinely national scale, more than 2,000 track miles under wire, stretching from New York down to Washington and west across Pennsylvania, finished in 1938. It carried express passenger trains at 100 miles an hour and heavy freight underneath the same catenary. It was the largest mainline electrification the country ever produced, and it is still standing today. But look at how it got built. The final push happened in the depths of the Depression, and it happened with federal money, through emergency loan programs created to put Americans back to work. The one American electrification that reached continental scale is the one where the government wrote a large part of the check, and a corporation without that check can be talked out of a purchase. Which brings us to the machine that did the talking. Here is the detail almost everyone misses about the American diesel locomotive. It is not really a diesel locomotive. There is no gearbox, no clutch, no drive shaft to the wheels. The engine spins a generator. The generator feeds electric traction motors mounted on the axles. Those motors are doing all the work, which means the thing that replaced the electric locomotive in America was, mechanically speaking, an electric locomotive. It simply carried its own power station on board. Think about what that did to the argument. Everything railroads loved about electrification, they suddenly got for free. Smooth torque from a standing start, no fire to build, no water stops, no ash pans to clean, dynamic braking that turned the traction motors into generators on a descending grade and held the train back without touching a brake shoe, and multiple unit control, so one crew could command 4 or 5 units at once. All of it, without a single mile of infrastructure. No towers, no substations, no transmission lines, no maintenance crews riding the wire in a blizzard at 2 in the morning. Once that machine existed, electrification in America stopped being a competitor. It became an expensive way to get something you could now buy in a box. Watch how quickly the wires came down. In the Cascades, the railroad shut off its electrification in 1956 and replaced it with something far cheaper. A fan house at the tunnel portal and a door that closed behind each train, blowing the diesel exhaust out. The problem that had once justified an entire electric division was solved by ventilation. On that Appalachian coal grade, the railroad bored a new tunnel with an easier profile around 1950, and the reason for the wire simply evaporated. When the Virginia Coal Road merged with its bigger rival at the end of the 1950s, the combined system had a parallel route with better grades, and the beautiful 1925 electrification went dark in 1962. Every time, the same logic. The wire had been installed to fix one specific thing. Fix that thing another way, and the wire becomes an expensive orphan. But cheap diesel and a fan house cannot be the whole story, because railroads elsewhere had diesels too and still put up catenary. Something else was pushing the American decision, and it has almost nothing to do with locomotives. It has to do with who owns the ground. An American freight railroad owns its track, its bridges, its tunnels, its signals, and the land underneath all of it. It maintains that infrastructure with its own money and pays property taxes on it. In most of the world, the state owns the rails and the railway operator simply runs trains over them. That difference changes what catenary is. For a state railway, overhead wire is a public work, financed the way a highway or a dam is financed, judged over 50 years. For an American railroad, it is a taxable private asset that has to earn a return in front of shareholders who will ask about it every quarter. And there is a subtler trap inside it. Diesel fuel is a variable cost. When freight volumes collapse in a recession, a railroad burns less fuel, parks locomotives, and its costs fall with its revenue. Catenary is a fixed cost. It has to be inspected, tensioned, repaired, and paid for whether the trains are running or not. In an industry that has ridden violent boom and bust cycles since the 19th century, converting variable cost into fixed cost is exactly the kind of thing that turns a bad year into bankruptcy. Then there is the geography problem, and it is worse than it sounds. Electrification only pays back if you can run electric locomotives end to end. The moment you reach the edge of the wire, you have to stop, uncouple, bring in diesels, and start over. That swap can cost an hour or more, and it happens in both directions, every day, forever. Which means partial electrification is not half a benefit. It is often no benefit at all. Now look at the American network. Trains routinely run 2,000 miles or more. Freight cars pass from one company's rails to another's and back again. Traffic is intensely dense on a few corridors and thin as thread across enormous stretches of the plains and the Mountain West. Wire pays where trains are frequent, and most American route miles are not. The railroad in Montana understood that problem better than anyone because it lived it. Its own electrification was crippled by the 200-mile hole in the middle of it. The system that should have been its greatest advantage forced a locomotive change twice on every through train. So the wires came down in the Cascades and in Appalachia and in Virginia. By the late 1960s, American freight electrification was almost gone, and then the price of oil quadrupled. If you are finding this interesting, hit subscribe. We cover locomotive history, railroad engineering, and the decisions behind the machines every week. The 1973 oil embargo should have been the moment the wires went back up. Suddenly, the entire economic case flipped. Diesel had been the cheap answer for 25 years, and overnight, it was not. The industry responded with a wave of studies, feasibility reports on eastern corridors, federal assessments of what nationwide electrification would cost and save, analyses of mountain districts in the West where heavy tonnage and steep grades made the numbers look best. Engineers built high-voltage test catenary at the government's Rail Test Center in Colorado. For most of a decade, it genuinely looked like American freight was about to get wired. And a handful of railroads actually did it. Out on the Navajo Nation in northern Arizona, a 78-mile line opened in 1973 to carry coal from a mine to a generating station. It had no connection to the national rail network at all, and it became the first railroad in the world electrified at 50,000 volts. That extreme voltage let the whole line be fed from the power plant itself, with no intermediate substations. It ran 3 loaded trains a day for more than 40 years. A similar coal shuttle went up in Ohio. Another opened in the early 1980s, running between Utah and Colorado, and a fourth in New Mexico. Every one of them is a closed system. One commodity, one origin, one destination, and a power plant sitting at the end of the line ready to sell electricity to its own railroad. Which tells you something important. The engineering was never the obstacle. Heavy electric freight worked beautifully in America whenever the conditions were pure. The trouble is that almost nothing about the real network is pure. And then the window closed. Oil prices came back down through the 1980s. The studies that had been commissioned in a panic were finished in a calmer market, and their payback calculations no longer held. Deregulation in 1980 gave railroads a far cheaper way to improve their finances than building infrastructure. Shed unprofitable branch lines, merge, and cut. The capital went there instead. Then came the double stack container, which let a train carry 2 layers of boxes instead of 1, and roughly doubled the value of every intermodal train. Railroads spent enormous sums raising bridges and lowering tunnel floors for the extra height, and many in the industry concluded that overhead wire and stacked containers were fundamentally at odds. That claim is contested. Both India and China run double-stack trains under catenary today, but the belief hardened at exactly the moment American railroads were deciding where to put their money, and it has never really softened. By 1981, the last electric freight train in the northeastern United States had run. The domestic manufacturers, with no market left, stopped building heavy electric freight locomotives altogether. The engineers who knew how to design them retired. The supply chain dissolved. That is how a technology dies in a country that already proved it works. Not in one dramatic decision, but in a chain of individually reasonable ones, each of which made the next one easier. So where does that leave the argument now? The industry's own trade association puts the cost of wiring the national network at around $1.1 trillion, which it describes as roughly 47 years of combined net income for all the major carriers. That number comes from the party with the least interest in finding electrification affordable, and independent estimates land far lower, often between $2 and $5 million per track mile, with only a fraction of the network worth wiring at all. But even the friendly numbers describe a project unlike anything a private American company has attempted in a century. The railroads also make a fair point about scale. Freight rail already moves a ton of goods hundreds of miles on a single gallon of fuel, and the entire American rail network accounts for well under 1% of national greenhouse gas emissions. Spending $1 trillion to shrink a very small number is a hard sell to anyone counting returns. So the industry is doing what it did in 1940. It is looking for a way to get the benefits of electric traction without the infrastructure. Battery locomotives are running in yard service and in trial consists on mountain grades, storing regenerative braking energy on the way down and giving it back on the way up. Hydrogen prototypes are being tested. Regulators in California have written rules that will eventually demand zero-emission locomotives, and the railroads are pushing back hard while quietly funding alternatives. Notice the shape of it. The same instinct that killed electrification the first time is the one steering the response now. Take the electric drive. Skip the wire. Carry the power source on board. It may work. Battery energy density is improving fast, and a hybrid that can charge under short sections of catenary on the steepest grades would be a genuinely American compromise. Electrify 5% of the route and let the machine handle the rest. But it is worth being honest about what was lost along the way. Those mountain electrifications were not failures. They were, by most measures, superb. Locomotives that could pull harder than anything burning coal, that never ran out of water, that fed power back into the wire on the way downhill and helped push the next train up the other side. Crews loved them. The engineering held up for half a century. They died because of arithmetic done by companies that owned the ground they ran on, in a country with cheap oil, on a network too big and too uneven to wire all at once. The next time you drive under a railroad bridge and look up at nothing but sky above the track, that emptiness is not an oversight. It is the accumulated result of 100 years of decisions, each one defensible on its own day, that together made America the only major freight railroading nation on Earth that runs almost entirely on liquid fuel. And out in Montana, those concrete stubs are still standing in the grass, in a straight line heading for the pass, holding up nothing at all.